And Matt's Selen, our wise guys, back with liquid nitrogen fun. We ran short last time on time, but you were telling us about the freezing the flowers and then they burst.
Right. So that was a bit of just having fun with flowers, at their expense, so to speak. But the whole point there was that it's when things are cold, the molecules that cause their smell don't leave them quite as easy, so you don't smell them as much. And you can illustrate the same thing by eating a marshmallow when it's warm. Go right ahead, just chomp down on it. Okay. And then I have another one here that I've frozen in the liquid nitrogen. Yeah. So what I want you to do with this one is take a bite of that one and see if it tastes different. Yeah, for real.
Yeah, there's no taste.
See, there's no taste. Now, you might think that it's not a good idea to stick something with that cold in your mouth, and it would be a terrible idea for just about anything. Yeah. But marshmallows, let's put it out, have a very low heat capacity.
How can you eat that?
Oh, it's fantastic. It's like ice cream. So anyways, now, the next thing we want to figure out is how the smell gets from over where the flowers come in the room to where your nose is, right? So they have to get through the air somehow. Right. And you can sort of illustrate this a little bit by, I have here some water. If you can sort of zoom in on that thing of water, I'm going to put a drop of food coloring in there. Okay. And you're going to see what the food coloring does as it goes in. Maybe you are.
Does it have that little safety cap on the top?
Oh, it's, okay. Blink. Okay, now if you kind of watch it, if you sort of watch, see how it spreads out sort of slowly, and this falls because it's a bit heavier.
Yeah, I'm going to turn it so we can get the lettering out.
But notice how it doesn't really spread very rapidly. It sort of goes down, and it's not until I take this thing...
It's kind of stuck in the middle.
Yeah, it looks like kind of a weird alien monster, actually.
Yeah,
and it's not until if I stir it up... There you got a picture of that? Doesn't that look cool?
That is cool.
Okay, and so you can sort of see that it sort of stays with itself and it very, very slowly goes around. If I wanted to get to the other side of the, if I want the smell, if the blue stuff is smell and the water represents the air in the room, I need to kind of stir things up a little bit. Yeah. Okay, and it turns out that the same thing happens in the air, and you can understand it in the following way just by thinking of atoms. That if some smell atom comes off the flower and it's way over there, it's got to get over to where your nose is. Now, the average speed of an atom in the air is about the same as the speed of sound, which is about 1,000 feet per second. Okay. So you would think that thing would be over in your nose right away. But it doesn't. It has a lot of little collisions, right? So what it does is it bumps into all the air molecules. So we can figure out how many air molecules it's going to bump into. Okay?
Really?
And you can, yes, of course we can. Awesome. So we're going to figure out that by looking at this balloon. So here's a balloon that I just blew up before I came in here. It's so big that it doesn't even fit in the screen. Yeah. And I also stuffed an identical one into the liquid nitrogen. Okay, what happens when you do that is that all the air inside becomes a liquid, and if you kind of zoom in on this, you might be able to sort of see that in the bottom of this, it's a little hard to tell, there's a little puddle of liquid air. Yeah. I'm going to put it over there because it's making a frightening noise. And so basically what you notice is that when you turn all the gas in a balloon into a liquid, which I did by sticking it in this very cold liquid here, then it takes up a lot less space than it does when it's in the balloon.
Sure.
It's about a factor of 1,000.
Really?
Okay, yeah. Okay. And so, in a liquid, suppose these were gas molecules in a liquid state. Okay. That looks pretty interesting, doesn't it?
It does.
The molecules are pretty much as close as they can in a liquid. You can't squish them anymore.
Got it, yeah.
If they become a gas, they get a little bit further apart, but in order to increase the volume by about a factor of 1,000, their separation only increases by about 10. Okay, because you have to cube that to get units of volume. So anyways, the point is that the molecules in air are pretty close together. And so they don't go very far before they have a collision with each other. That's a scary sound, isn't it?
Sounds like it's about to burst.
In fact, I got another one. I got Illini patriotic balloons in here, so I can wish that one out too. Okay, and so that's why it takes a very long time. It would take a long time for the smell to get from there to your nose because it runs into an air molecule within a distance of about 10 atomic diameters. So it's it has a lot of collisions, and it would take hours for the smell to get from one side of the room to the other if the air wasn't moving around. But of course the air is moving around because people walk through the room and so on. So it's sort of like a big air soup. Yeah.
Yeah. Speaking of walking around, Robert Reese just finished with his little radio duties.
Want to have a treat?
Now, did you try one of these frozen marshmallows earlier?
Oh, they're great.
I would think that it would stick to your tongue, like a flagpole.
Very low heat capacity, so it's pretty safe. You would never do that with anything else that was that cold, but marshmallows, you can do it.
It's really odd, isn't it?
Isn't that bad? And now you get sort of a vapor coming up through your nose. It's the funnest thing ever. Watch.
This is way too much fun. I'd love to be in your class. That would be awesome.
I'm not so good at that.
That's okay.
Well, anyways, that's all about diffusion. And I think
Your balloons came out. Now, this balloon came out all the way back to its original
so that's the one that was frozen. You notice that when it came out of here, it was pretty small.
Yeah.
When now that all the air that was liquid inside it has expanded back into a gas, this thing is much bigger than it was.
Yeah.
Okay, so that's that factor of about 1,000 in volume is what we use to figure out the average spacing between atoms in the gas. And actually, the way that the molecules jostle and bump into each other as they come from over there to over here is a fascinating thing. It's called a random walk motion, and I think maybe we'll do a whole WCIA thing on randomness and random motion at some point, maybe pretty soon, because that's very fascinating, and it's something that people might want to understand.
Okay.
Awesome, Mats. Well, thanks for coming in, bringing the play toys. We appreciate it. That's a lot of fun today.
Yeah, I'll leave this for you if you want, Robert.
Sweet.
Yeah, we'll find a use. We'll find a use for it. Trust me. All right. If you want to see a replay of this segment or Matt's previous segment, real easy. Go to our website, IllinoisHomepage.net.